Hey everybody, this short video will walk us just through classical measurement error in X. Since I'm going to be focused on walking through the formulas on the board, I'm just going to move the camera so that everything you can see is the board. I'm going to use as a running example for this a wage equation where we're interested in the effect of schooling on wages, but we are concerned that we have measurement error in schooling. So the actual model that we'd like to run to find the true relationship between schooling and wages is this. Log wages is alpha times SI star, which is our true level of schooling. And epsilon I is a well-behaved error term. The issue with measurement error in X is that we're concerned that the variable that we've got is not measured correctly. And so when we deal with measurement error, we usually need to give some special names to the regular and the mismeasured variable. So our true variables are going to be labeled with stars. But our observed variable is going to just be SI, which is related to, but just not identical to, the true level of education. It's the true level of education plus an error. And keep in mind the error could be positive or negative. And so VI is, again, a well-behaved error term. It's a mean zero error term. But it suggests that SI is not dependable as a measure of SI star. What I want to do now is just walk through what the consequences are of using SI instead of SI star in the regression. Essentially, I want to walk through what the true regression should be and then what it actually is. And so the first thing I want to do is I'm just going to make a substitution. Where this SI star is, I'm going to put what SI star actually is when there's this measurement error situation. So if you just rearrange this, SI star is the measured SI minus this error, whatever it is. So if we wanted to rewrite, we know that when we do the equation, we actually have SI and an error in here. But of course, if you're running the regression, you don't have VI, that's an unobservable. And so what it looks like to you as you're doing the analysis is, well, you've got SI, you've got an error term, but then your error term is actually compounded because VI is also unobserved. We need to carry through the alpha, so we have minus alpha VI here. So if we're trying to think about what the problem is, you can see the whole nature of the problem right here is alpha is hanging out in more than one place. Alpha is in the error term buried, and it's also out here being estimated. And so probably your intuition tells you that if you simply run this regression on the mismeasured variable SI, you can't rely on the alpha that you're going to get as the slope. So what I want to do is just walk you through exactly what's wrong with the alpha hat that you're going to get if you run this regression. This just requires us walking through a couple rounds of looking at the p-lim of alpha. You may not have done this in a while. Hopefully it's familiar that the regression coefficient in a standard OLS regression is equal to x prime x inverse x prime y. Luckily, we're doing a bivariate regression, so we don't really need to use matrices right now. All I'm going to do is just put the xy piece on the top and the x squared piece on the bottom. A little bit more like covariance over variance, which is what it boils down to in 2 dimensions. And so up here, we have 1 over n times the sum of essentially x times y, si, times log wi. On the bottom, we have 1 over n times the sum of si squared. Again, this is basically covariance over variance. So if we want to look at the limit of this, what we would like the limit of alpha hat to be is, of course, alpha. That would mean we have a consistent estimator. And so what we're going to do is we're going to identify exactly what's wrong here and why we can't be confident that alpha hat's doing a good job of estimating alpha for us. So first thing I'm going to do is I'm just going to write out in terms of SI star each of these pieces. because that'll get us at the true values so that we can see if the p-lim of alpha hat gets us to the true alpha that goes with the SI stars. And so the top p-lim, we're going to replace SI with SI star plus VI. And then we're going to replace the log of WI with the true value, which is the original equation, alpha SI star plus epsilon I. For the denominator, we can have p-lim and then sum, and we're simply going to write this out, SI star plus VI squared. This is a little bit ugly when we multiply it out, but I want to make sure that you're following where the intuition is going to come from here. And so we're going to walk through the math as well. We're going to actually multiply this out. You can use FOIL like you learned in middle school. Alpha SI star squared plus SI star epsilon I plus alpha SI star VI plus epsilon VI. Epsilon I VI. Big ugly equation. On the bottom, again, we're going to actually square these things. And so we get SI star squared plus 2 SI star VI plus VI squared. Now, what we'd love to do is do some canceling. The way to get at any canceling in this context is to make some mutual independence assumptions. This is where that sort of classical piece kicks in. If we want to think about the kind of measurement error that we have some idea of how to think about, classical measurement error is it. Classical measurement error has mean 0, and the error itself isn't correlated with anything else. It's just random error, well-behaved error. And so we're going to assume that the S star, the epsilon, and the V are mutually independent. So knowing what someone's true SI star is would not give you any clue into whether there's any measurement error. This clearly rules out anything where people are purposely reporting incorrectly based on the level of their S star. And so we've just got random error in the regular sense, epsilon. We've got random measurement error, V. Neither of them is correlated with S star. If we make these assumptions, then a lot of this stuff can actually cancel out. And so I'm going to show you what you end up with. We end up with the p-lim of alpha hat equal to, in the numerator, the p-lim of 1 over n sum of alpha SI star squared over the p-lim of 1 over n, the sum of SI star squared plus VI star squared. Those middle terms fall out. We can simplify this a little bit further. Same numerator, but we can break up the denominator, and this gets helpful. So 1 over n sum of SI star squared plus 1 over n sum of VI squared. Okay, what I want you to notice at this point is this right here. If that was all we had, we could clearly just cancel it out and we would have alpha. We want the p-lim of alpha hat to be alpha. That would mean that we're fine. So the problem comes down to the measurement error here, throwing a wrench in that, not allowing us to be able to do that cancellation because it's in this denominator, and so it's all stuck together. If we do a divide through by sum of SI star squared, we can get a final version of what this p-lim looks like. It's ugly enough that I want to make sure that I write it nice and big here so that we can see what the consequence of the measurement error is. So we're going to divide through. And what we end up with is that the p-lim of alpha hat is alpha over 1. That's the part where if we could just leave it alone, we'd have it doing exactly what we want it to do. But it's actually 1 plus, and then this whole piece. 1 over n sum of vi squared over 1 over n sum of si star squared. So the question becomes, what is the deal with this? This piece right here is, by necessity, because both pieces are squared, positive. So this thing is positive. What that means is this alpha over 1 plus something really is plus something. And so we've got something that is less than alpha. This gets us to the most important piece to remember about measurement error in X when it's classical, which is that alpha hat that you get when you run the regression underestimates alpha.